What would you think if you had a magical box that could create anything you want, from delicious food, your favorite toy, or even mythical creatures that only exist in legends? The only amazing thing here is that the box doesn't decide what to create until you open it and look inside. In other words, before you look inside, it could be creating anything. It's only when you open the box that it chooses and becomes just one thing: the food you love, the toy you've longed for, and the mythical creature. All these possibilities are contained within the box, and its mechanism works similarly to how particles behave in quantum mechanics. In this video, let's explore the mysterious box to connect the dots and shed light on part of the nature of the universe, which since ancient times the Greeks proposed as being made up of the basic elements of air, fire, and water, the fundamental components of everything around us. So before we continue with the video and explore this interesting topic further, don't forget to like, subscribe to the Top Hidden Knowledge channel to stay updated on everything related to personal and spiritual growth. This helps us bring more content that can make a difference for you. In our story, the act of opening the magical box and looking inside is analogous to observing a quantum particle, forcing it to become just one thing. Before you observe it, the possibilities are endless, much like a particle existing in a superposition of states in quantum mechanics. The moment you observe it, however, it collapses into a single state, much like the box choosing to present only one of its potential creations, whether it be an apple, a pencil, or a unicorn. This is a crucial point that leads us into an exploration of the nature of reality itself. Historically, the ancient Greeks proposed that the fundamental elements of the universe were air, fire, and water. This idea was revolutionary at the time, offering an attempt to explain the diversity and complexity of nature through a limited set of substances. While their understanding was limited by the tools and knowledge of their time, their ideas laid the groundwork for future discoveries. Fast forward to a century ago, and physicists were sure that the atom was the fundamental building block of matter. Atoms, consisting of a dense nucleus of protons and neutrons with electrons orbiting around them, were considered the smallest indivisible components of matter. However, experiments conducted by great scientists such as Max Planck, Albert Einstein, Niels Bohr, and others revealed something startling. Atoms themselves are made of even smaller particles. These particles, electrons, protons, and neutrons, exhibited behaviors that classical physics couldn't explain, leading to the birth of quantum mechanics. The behavior of these particles, such as their ability to exist in multiple states at once, superposition, and to be entangled with each other, challenged everything we thought we knew about the world. Modern physics has since advanced our understanding of the universe. We now know that the fundamental building blocks of the cosmos are subatomic particles, such as electrons, quarks, and neutrinos. These particles are believed to be the true constituents of matter, and everything we see around us is made up of various combinations of these particles. But even this understanding doesn't fully explain reality. Quantum theory reveals that the building blocks of the universe extend far beyond just particles. They include the very fabric of space and time itself. In the quantum framework, the universe is not just a collection of particles moving through space. Instead, it is a dynamic interplay of fields and forces that make up the structure of space-time. These fields, described by quantum field theory, are the true essence of what constitutes reality. Particles are not distinct objects, but are considered excitations or disturbances within these underlying fields. Think of these fields as the fabric that holds everything together, with particles emerging as the ripples within these fields. In essence, particles are the manifestations of these fields when they are excited in specific ways. This understanding of the universe is deeply counterintuitive to our everyday experience. We are used to thinking of particles as solid, individual objects, but quantum theory shows us that the true nature of matter is far more complex. Today, we believe the deepest layer of reality consists of these elementary particles governed by quantum theory. This is an invisible realm that we cannot directly observe with our senses, but it is the foundation upon which all visible matter is built. Let's start by looking at what we know. Visible matter is made up of atoms, and atoms consist of a nucleus containing protons and neutrons, surrounded by electrons. However, protons and neutrons are not the smallest components of matter. According to the standard model of particle physics, the protons and neutrons themselves are made of even smaller particles, quarks. These quarks combine in specific ways to form protons and neutrons, which in turn make up atoms. Even the electron, which orbits the nucleus, is considered an elementary particle in itself. The surprising thing is that everything in the universe can be traced back to atoms. An atom is the smallest unit of matter that retains the properties and characteristics of the larger, visible world, including its physical and chemical properties. But an atom is not simply a solid, indivisible unit. It is, at its core, a quantum entity with its own energy levels, properties, and laws of conservation. It interacts with the four known fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. In fact, all of physics can be understood by studying the behavior of atoms and the particles that make them up. Atoms, as we know them, are far from the ultimate end of the story. Modern physics has revealed that atoms themselves are not static, immutable objects. Instead, they are dynamic systems governed by the strange and unpredictable rules of quantum mechanics. An atom exists in a state where its exact position and velocity cannot be precisely determined at the same time, a concept known as Heisenberg's uncertainty principle. This is because the electron, which orbits the nucleus, doesn't have a definite position or velocity in the traditional sense. Instead, it exists in a cloud of probabilities, where the likelihood of finding it in a particular location is determined by a probability wave. The act of observing the electron forces it to choose a specific location, collapsing the probability wave into a definite state. This is one of the foundational ideas of quantum mechanics. The act of observation or measurement changes the state of the system. Before observation, the system exists in multiple possible states. Once we observe it, we collapse the superposition into a single, definite state. This process, known as wave function collapse, is one of the many strange and puzzling aspects of quantum theory. But this is where the story becomes even more fascinating. Quantum mechanics suggests that the universe operates not just in terms of particles, but as a network of interconnected fields. These fields are the fundamental entities that govern the behavior of matter and energy. Particles, like electrons, emerge as excitations in these fields, much like a wave appears as an excitation in the water. Instead of thinking of the universe as a collection of isolated particles moving through space, we must begin to think of it as a complex, dynamic system of fields that are constantly interacting and shaping reality. This shift in perspective fundamentally alters our understanding of reality. The universe is not made up of solid, distinct objects, but rather is a continuous field of energy, with particles emerging as manifestations of that energy. It is only when we interact with these fields, whether through observation, measurement, or other forms of engagement, that reality as we know it collapses into the familiar forms we perceive in our everyday lives. In conclusion, the story of the universe is far more intricate and dynamic than we once believed. What we thought were solid, indivisible objects are actually intricate manifestations of underlying fields. These fields interact with one another in complex ways to create the reality we experience. Quantum theory challenges our fundamental perceptions of reality, suggesting that the universe is a dynamic, interconnected whole, where the smallest building blocks of matter are not isolated particles, but are part of a larger, more intricate system of energy and information. The more we explore the depths of quantum theory, the more we realize that the universe is far stranger and far more fascinating than we could have ever imagined. Atoms have long been central to our understanding of the universe. On Earth, about 90 elements occur naturally, formed by cosmic processes such as stellar fusion and supernova. Each of these elements is composed of atoms with a nucleus made of protons and, in many cases, neutrons, surrounded by electrons that balance the number of protons in the nucleus. The protons, neutrons, and electrons are the primary subatomic particles that define the structure and behavior of atoms. What is fascinating about atoms is that despite their vast variety, there is only one key property that defines each type of atom: the number of protons in the nucleus. This is what determines the element itself, whether it's oxygen, carbon, iron, or any other element, and consequently, it dictates the many unique properties of that element, such as hardness, color, melting and boiling points, density, conductivity, electronegativity, and ionization energy. For example, carbon atoms form the basis of all life as we know it, with properties that allow them to bond in complex structures like DNA and proteins. Iron, on the other hand, forms the backbone of materials with high strength and conductivity. These distinct characteristics arise solely because of the atomic structure, specifically the number of protons in the nucleus. In our daily lives, we often take certain rules for granted, such as the relationship between cause and effect. We expect that if one event occurs, it will lead to another, and depending on the circumstances, different causes lead to different effects. This is the deterministic worldview that governs much of classical physics, where outcomes are predictable if we know the initial conditions. However, in quantum mechanics, the rules are fundamentally different. The first striking realization in the quantum realm is that even the starting point of a system cannot be defined with arbitrary precision. This is because of the inherent uncertainty present in quantum systems. Unlike classical physics, which describes systems in deterministic terms, quantum physics introduces a level of unpredictability. In quantum mechanics, it is impossible to know all properties of a system with complete certainty at the same time. Heisenberg's uncertainty principle is a key aspect of this. It states that certain pairs of properties, such as a particle's position and momentum, cannot be simultaneously measured with perfect precision. The more accurately one property is known, the less precisely the other can be determined. In classical physics, if we know the starting conditions of a system, its position, speed, and forces acting upon it, we can predict its future behavior with certainty. However, quantum mechanics tells us that we can only calculate probabilities. Instead of being able to describe a quantum system with absolute precision, we deal with a range of possible outcomes. This doesn't mean that the system is random or chaotic. It means that the future of the system is not deterministic, but probabilistic. We can calculate the probabilities of different outcomes occurring, and if we make a precise enough measurement or observation, we will see a single result. But here's the twist. The act of measurement or observation itself changes the state of the system. This phenomenon, known as wave function collapse, is one of the most perplexing aspects of quantum mechanics. A particle can exist in a superposition of multiple states, meaning it can be in more than one state at the same time. For instance, it could be in two places at once or moving in multiple directions at the same time. However, when we measure, The superposition collapses and the particle chooses a single state. This behavior is not just theoretical. It has been observed in experiments involving electrons, photons, and other quantum entities. For nearly a century, physicists have debated the implications of this observation. The strange thing is that the very act of observing a quantum system forces it into one definite state. But how and why this happens is still a matter of great debate. One famous thought experiment that captures this paradox is Schrödinger's cat. In 1935, physicist Erwin Schrödinger devised this experiment to highlight the counterintuitive nature of quantum theory. He imagined a cat inside a sealed box with a vial of poison. The poison was linked to the decay of a radioactive atom, so if the atom decayed, it would trigger the release of the poison and kill the cat. However, according to quantum mechanics, until the atom's state is observed, it exists in a superposition of decayed and not decayed. This means that the cat, too, would be both dead and alive at the same time until the box is opened and the cat is observed. The act of observation forces the superposition to collapse, and the cat is either dead or alive. This paradox brought quantum weirdness into the macroscopic world and forced researchers to grapple with the implications of quantum mechanics on everyday objects. Physicists now refer to these large-scale superpositions involving multiple atoms or quantum entities as Schrödinger's cat states. These states challenge our classical understanding of reality. In the quantum world, particles can exist in multiple states simultaneously, creating a reality where the boundaries between what is real and what is possible become blurred. Quantum mechanics, while supremely effective in describing the microscopic world of atoms and their constituents, also reveals a reality that defies intuition. Particles can behave both like waves and particles, and the very act of measurement influences their behavior. This wave-particle duality and the superposition of states challenge our conventional ideas about how the universe operates. For example, we are used to thinking of particles as individual, discrete objects, but in the quantum world, particles are better understood as excitations or disturbances in fields. These fields are the true building blocks of reality, and particles emerge as specific manifestations of these fields when they are excited in particular ways. Quantum mechanics tells us that particles are not solid objects moving through space in a predictable manner. Instead, the universe is a dynamic interplay of fields and forces within the structure of space-time. The true essence of reality lies in these fields, and particles are simply the emergent excitations within these fields. This framework not only reshapes our understanding of matter, but also challenges our perceptions of space, time, and the very nature of reality itself. In summary, atoms and their behavior in quantum mechanics give us profound insights into the nature of the universe. While atoms have long been considered the building blocks of matter, quantum theory reveals that the universe is far more complex and interconnected than we ever imagined. The uncertainty and superposition that govern quantum systems suggest a reality that is probabilistic, not deterministic. The act of observation and measurement plays a crucial role in shaping the outcomes of quantum systems. These insights have revolutionized our understanding of the universe, revealing a reality that is far stranger and more intricate than we can easily comprehend. The quantum world, with its strange behaviors and counterintuitive nature, is still one of the most profound discoveries of modern science, inviting us to reconsider everything we thought we knew about the universe. In the past decade, the study of quantum systems, often using Schrödinger's famous cat thought experiment, has been a key tool for researchers exploring the boundary between the quantum world and the classical world we experience. These cats have provided insights into why we don't see everyday objects existing in two states at once, and whether it's even possible for us to observe such phenomena in the future. The idea that a quantum animal could simultaneously be both alive and dead is one of the most striking and perplexing examples of what is often called quantum weirdness. The questions raised by quantum physics, such as how or why does quantum physics work, and what, if anything, do the mathematical objects in quantum theory represent, seem to have as many answers as there are people willing to explore. In them, however, these answers often say much more about our own biases, prejudices, and assumptions about how the universe should work than about the universe itself. The reality of the quantum world challenges our deepest assumptions about how things operate on the most fundamental level, leading us to reconsider the very nature of existence. One of the core challenges in understanding quantum physics is that, unlike classical physics, there are very few things we can actually observe directly in nature. When we look at particles, we can observe certain properties, like position, momentum, cross-sections, scattering amplitudes, and individual quantum states. But even these measurements come with inherent limitations. In classical physics, we tend to assume that the underlying nature of reality follows predictable, intuitive rules. But quantum mechanics suggests the opposite. The universe may be governed by rules that are completely foreign to our usual ways of thinking. Our senses and capabilities are limited, so our perception of reality is inherently biased by our own limitations. The true rules governing the universe may be far more abstract and unintuitive than we can possibly imagine. We often talk about particles as if they occupy fixed points in space, but quantum theory tells us that this isn't entirely accurate. In reality, particles are better understood as energetic spikes or excitations in underlying quantum fields. For example, a photon is an excitation of the electromagnetic field. These quantum fields permeate the entire universe, meaning that there is always some form of residual foam throughout space. These so-called virtual particles appear briefly and vanish, even in the absence of enough energy to create a real particle. Virtual particles may seem abstract, but they represent the complex, dynamic nature of the quantum field, suggesting that reality is far from the solid, stable picture that our everyday experiences might lead us to believe. Fields are considered more fundamental than particles because they provide the mathematical framework that makes sense of quantum mechanics. The theory of quantum fields tells us that particles emerge as localized excitations within these fields. Without the underlying quantum fields, particles wouldn't exist in the form we recognize them. However, the quantum nature of a field itself means it can't be observed directly in the same way we observe particles. Any observation of a field requires energy, and that energy forces the field to produce a particle. This is why we tend to focus on particles, because they are the visible manifestation of the underlying quantum field, something we can actually detect and measure. One of the most intriguing aspects of quantum physics is the concept of antimatter. For nearly every particle, there is a corresponding antiparticle with the same mass but an opposite charge. While antimatter is rare in the visible universe, it is typically produced in particle collisions. The existence of antimatter presents a mystery, as the universe is overwhelmingly made of matter. This imbalance between matter and antimatter is one of the great unsolved questions in physics. Why does the universe seem to be made mostly of matter, while antimatter is so scarce? The quantum world operates by rules that seem completely counterintuitive, defying common sense in profound ways. For instance, particles can behave like waves under certain conditions, and even the very concept of a particle becomes uncertain when we examine it closely. This is where Heisenberg's uncertainty principle comes in. It tells us that the more precisely we try to pinpoint a particle's location, the more uncertain we become about its momentum. Similarly, the more precisely we measure its momentum, the less we know about its exact position. This is a fundamental property of quantum systems. Their properties are inherently fuzzy and cannot be known with perfect precision at the same time. Heisenberg's uncertainty principle suggests that these uncertainties are not just the result of experimental limitations or our inability to measure things perfectly. They are intrinsic to the nature of quantum systems. It implies that the very act of measurement alters the system being observed. This is one of the most puzzling aspects of quantum mechanics. How can something as fundamental as the measurement process influence the outcome of an experiment? Why does the act of observation force a quantum system to take on a definite state when it could have existed in a superposition of multiple states? These strange behaviors are not just theoretical concepts. They have been confirmed through experiments that demonstrate the strange and non-intuitive nature of quantum mechanics. For example, the double slit experiment, one of the most famous demonstrations of quantum weirdness, shows that particles like electrons can behave like waves, interfering with themselves, creating patterns that suggest they are passing through multiple slits simultaneously. This behavior only becomes clear when we observe the particles, and once we measure them, they collapse into a definite position. Before the observation, however, the particles exist in a state of probability, behaving as if they are in multiple places at once. The implications of these discoveries extend far beyond the microscopic world. Quantum mechanics is not just a set of abstract mathematical equations. It provides a framework for understanding the very fabric of reality. It suggests that at the most fundamental level, the universe is not made up of isolated, static particles, but is instead a dynamic, interconnected system of fields and forces. Matter, energy, and space are all manifestations of underlying quantum fields, which are constantly fluctuating and interacting. In conclusion, quantum mechanics forces us to rethink our most basic assumptions about the nature of the universe. It reveals a world that is profoundly different from our everyday experiences, where particles can exist in multiple states at once, and where the act of observation plays a central role in determining reality. The quantum world is full of paradoxes and strange behaviors, but it also offers a deeper understanding of the universe, one that transcends classical physics and opens up new possibilities for exploring the mysteries of existence. The more we delve into the quantum realm, the more we realize that the universe is far stranger and far more interconnected than we ever imagined. The most surprising aspect of quantum physics is the minimal properties needed to define a particle: mass, charge, and angular momentum or spin. With these, a mathematical equation can describe the particle fully through its wave function, which predicts its behavior probabilities. This concept is closely linked to wave-particle duality and superposition. Particles exist in a wave-like range of states until observed, at which point their wave function collapses and they adopt a specific state. However, the question of who or what is needed to observe this collapse remains unanswered. Do detectors suffice, or does human consciousness play a role? Quantum physicists have proposed various interpretations, from the necessity of human consciousness to the idea that wave function collapse is illusory and all possible states exist in parallel. Universes, the many worlds interpretation. There is no straightforward answer. We learned what we know today about the universe by asking the right questions, which means by setting up physical systems and then performing the necessary measurements and observations to determine what the universe is doing despite what we might have intuited beforehand. The universe showed us that the rules it obeys are bizarre but consistent. The rules are just profoundly and fundamentally different from anything we'd ever seen before. Reality, if you want to call it that, isn't some objective existence beyond what's measurable or observable in physics. Describing what is observable and measurable as accurately and completely as possible is our highest goal. By creating a theory where quantum operators act on quantum wave functions, we can accurately calculate the probability distribution of possible outcomes. For most physicists, this is enough. However, you can add assumptions to these equations and come up with different interpretations of quantum mechanics. Is the quantum wave function meaningless until you make a measurement? Do all possible outcomes occur, requiring an infinite number of parallel universes? Can reality be imagined as an infinite number of identically prepared systems with measurement, choosing which one represents our reality? Do particles always have real, unambiguous positions, guided by deterministic pilot waves in a non-local manner? There are various quantum interpretations with different assumptions about properties. Despite their differences, no experiments can distinguish these interpretations from each other. Although certain interpretations, like those with local real, deterministic hidden variables, can be ruled out. Frustratingly, all of these interpretations, plus others, are experimentally indistinguishable from one another. There is no experiment we have been able to design or perform that discerns one of these interpretations from another, and therefore they are physically identical. The idea that there is a fundamental, objective, observer-independent reality is an assumption with no evidence behind it. Just thousands upon thousands of years of our intuition telling us it should be so. Science doesn't aim to confirm our biases, but seeks to uncover the nature of reality, regardless of our preconceptions. To understand quantum mechanics, we should let go of biases and embrace what the universe tells us. Entangled photons emitted from a source, reaching separate observers, exhibit random results but display correlations. Whether these correlations follow local realism or not depends on whether they obey or violate Bell's inequality. Understanding. The universe isn't about revealing a true reality separate from observers' measurements and interactions. Reality might be intertwined with measurement, observation, and interaction at a fundamental level. To further understand the universe, we need experimental tests to distinguish between interpretations. So far, only interpretations that require local realism have been ruled out. Choosing between interpretations is a matter of aesthetics. Experimental measurements of polarization correlation agree with theoretical predictions from quantum mechanics, indicating that local real correlations between photons cannot explain the observed precision. In science, we don't declare what reality is and then adjust observations to fit our assumptions. Theories and models that predict observations with accuracy, predictive power, and minimal assumptions survive. Physics isn't troubled by reality seeming puzzling and bizarre. The issue arises only if we demand more from the universe than reality provides. There's a strange and wonderful reality out there. Until we devise experiments that teach us more, it's better to embrace reality as we can measure it than to impose additional structures based on our biases. Until we conduct that crucial experiment, we'll be philosophizing superficially instead of relying on scientific intervention. We'll remain in the dark. Until then, quantum mechanics stands as science's most precise and powerful theory of reality, predicting countless experiments and spawning numerous applications. However, physicists and philosophers remain divided over its interpretation. Many physicists, perhaps the majority, adhere to the Copenhagen interpretation, which suggests physicists should focus on calculations rather than trying to understand the underlying meaning of quantum mechanics. Philosopher Tim Maudlin criticizes this approach, highlighting several interpretations of quantum mechanics that offer detailed explanations of how the world functions. Yet other scientists' scrutiny of these interpretations reinforces skepticism, as they appear convoluted and implausible. They don't explore interpretations that frame quantum mechanics as a theory about information, which some find appealing. However, to others, these information-based interpretations seem even less plausible, as they introduce consciousness into physics, undermining its objectivity. The debate over consciousness is similarly contentious. Previously, there was a consensus that consciousness emerges from neural processes, but empirical evidence for these theories has been lacking. Consequently, there's now a multitude of theories, including integrated information theory and proposals suggesting quantum effects underpin consciousness, although evidence for the latter is sparse. Moving on, the journey into understanding quantum reality goes beyond the limitations of our rudimentary perceptions. It's easy to be seduced by the face nature reveals directly to our senses. Evidence gathered from our rudimentary perceptions often yields a clouded conception of the world we inhabit. Assessing existence while failing to embrace the insights of modern physics would be like wrestling in the dark with an unknown opponent. By deepening our understanding of the true nature of physical reality, we profoundly reconfigure our sense of ourselves and our experience of the universe. Quantum physics is captivating because it defies our everyday experiences. Matter can behave as both waves and particles. The universe is composed of indivisible quanta. We can only predict probabilities rather than specific outcomes, and it operates non-locally in both space and time. Its effects are most apparent on the smallest scales, making it one of the most peculiar discoveries about the universe. Yet we often incorporate ourselves into the equation, introducing concepts like observation, measurement, and interaction. Remove ourselves, and we're left with equations, results, and the universe's answers. Physics can't explain why the universe works as it does. It can only elucidate how it functions. To understand the fundamental nature of reality, ask the universe questions about itself and heed its responses. Anything else we add is our own construct, not the universe's. What do you think about the insights shared above? Do you believe there is a clear intersection between science and spirituality or human faith? After watching this video, how do you think your perspective on reality will change? Feel free to share your thoughts in the comments. Thank you for watching. If you learned something from this video, please like, subscribe to the Top Hidden Knowledge channel for more content on wisdom, spirituality, and personal growth. Or, if you have time, check out other videos on this channel. Until next time.